Hello everyone, thanks for tuning in. I'm Adithya Bhat, a third year PhD student from Purdue University. Today I'll be talking about our work, Reparo, a publicly verifiable repair layer for blockchains. This work is in collaboration with Sri AravindaKrishnan, Bernardo, Daniel, and my advisor Aniket. First, let us take a look at why we need repairable blockchains. Here are some examples of ethers that were affected by bugs. This is the famous second parity multisig wallet hack. There are even t-shirts with "Oops, I accidentally killed it" text for sale. This is the patch that Ethereum used to fix the DAO hack. This is the first parity multisig wallet hack. This is the Quadriga CX bug where the contract address was computed incorrectly due to a change of API. This is another bug discovered in the Ethereum JavaScript library which computed the address of a wallet incorrectly. This is a user whose funds got stuck because of the bug in the Ethereum JavaScript library. This is a bug in the client implementation which forgot to add a to field to the transaction. Ethereum treats such transactions as a contract creation transaction, and this results in a contract with no code in it, leaving the ether sent in the transaction in a state of limbo. This is a scenario where a user sent money to a handwritten address but was off by 1 byte. This is a bug in the Rex MLS contract where a wrong contract address was hard-coded. So far, at least 4.3 million ethers worth around 8 billion US dollars were affected due to bugs in smart contracts or associated libraries. Currently, there are no mechanisms in place to recover them. We can't keep emailing the Ethereum Foundation every time there's a mistake. Even our banks have mechanisms to roll back accidental transactions, and so it is natural for us to expect the same from decentralized crypto. Before we dive into Reparo, let us take a look at some of the approaches taken by recent works on repairable blockchains. In general, there are two approaches to transform an immutable blockchain into a repairable blockchain. The first approach is to use cryptographic tools such as attribute-based encryption, Chameleon hash functions, or other MPC techniques. The second approach is to use pure consensus to securely repair transactions. In this approach, we change the blockchain protocol itself to be aware of repairs and react to repairs accordingly. We will evaluate some of the related works using the following metrics. Stateful repairs. By this, we ask if we can repair transactions that result in a different final state. System scale MPC. By this, we ask if we need all the miners or deciders of the system to come together and participate in some protocol. Repairability of existing contents, or REC in short. With this metric, we ask if after deploying the solution on an existing blockchain, say for instance Bitcoin or Ethereum, can we start repairing transactions prior to introducing the proposed solution? In simpler words, we ask if the solution is introduced in, say, block 5000, can we repair transactions made before block 5000? As we will see, there are several solutions who enable repairs of transactions in the blocks produced after introducing the solution. That is, in this example, you can repair transactions, possibly using special transactions, only made after block 5000. The final metric is public verifiability. By this metric, we ask if every node in the blockchain can see who triggered the repair and who supported the repairs. The work by Atanasi et al. In 2017 was the first work to build a redactable blockchain. It allows redacting illicit contents from the chain. it uses Chameleon hash functions to perform reductions. A Chameleon hash function ch is an extended notion of the hash function with the following properties. For every function ch, there is a trapdoor tau. For every function ch, there is a hashing key k. Anyone with the hashing key k can generate the hash function. The owner of the trapdoor keys, tau, can find collisions in the domain of the hash function ch. With this introduction, we see that this work uses Chameleon hash functions and an MPC protocol between the miners where they use the trapdoor tau to redact contents. It only supports redactions and does not support stateful repairs. To implement it in Bitcoin or Ethereum, the system should use the Chameleon hash functions, which means that we cannot apply it to repair old transactions. Therefore, it does not support REC. Finally, this solution does not have public verifiability as nodes in the blockchain do not know which transaction changed or who supported the repair. Puddu et al. In 2017 proposed a solution where they introduced two new types of transactions, mutable and meta transactions. All mutable transactions can be set to no-op transactions. It requires the miners or validators to not distribute the decryption keys to redacted data. Another drawback of both of these approaches is that a transaction cannot be repaired if the sender or senders of the transactions do not cooperate or refuse to help with the repair. Therefore, for instance, if an attack drained the funds from a smart contract, we cannot repair the transaction without the support of the attacker. Derler et al. In 2019 proposed a solution using policy-based attribute-based encryption and Chameleon hash functions. A transaction can be changed by a set of miners as per the policy. In this technique, no large-scale MPC among the miners is required. This protocol lacks public verifiability. It also requires modifications to how the Merkle roots are computed in the blocks. Hence, it does not guarantee REC. Duber et al. 2019 proposed a solution to perform stateless repairs using two hash links in the block header. It also uses on-chain voting to decide whether or not to apply the repair. This makes their solution publicly verifiable. Their solution does not require any protocol to be run between the miners. However, the proposed changes in block header structure do not allow repairability of existing transactions since they break the hash chain. Their solution is also only applicable to stateless repairs. Tezos is a self-amending crypto ledger. This solution has stakeholders that can propose and amend changes to the blockchain and the amendment process itself. This solution is therefore publicly verifiable. Tezos also allows stateful repairs to the blockchain without needing any protocol to be run between the miners. Tezos is a new blockchain. It cannot be implemented on Ethereum or Bitcoin to start repairing old transactions. Finally, we present our work, Reparo, which allows stateful repairs without needing any complex cryptography or MPC, while allowing repairability of existing contents and public verifiability of repairs. Now, let us start exploring Reparo. Reparo uses an underlying blockchain and transforms it into a repairable blockchain by overriding the validate chain and validate block functions of the underlying blockchain. Reparo is a mechanism to validate repaired chains, and therefore it works for repairs done at any point in the lifetime of the blockchain. Reparo can even allow stateful changes, as a state change is a mechanism to validate hash and state links in the blockchain. Unlike some cryptography-based solutions, such as Chameleon hashes, Reparo allows repairs any number of times. The repairs performed using Reparo is also publicly verifiable. Before we go into the solution of Reparo, let us first see why some naive solutions don't work for fixing smart contract bugs. A natural question that one can ask is, what about hard forks? Hard forks are historically arbitrary in nature. For instance, in Ethereum, tau was considered a big enough bug to fix it via hard fork, but later bugs such as the parity multisig bugs were simply ignored. The second problem is that hard forks require support from the miners, because a hard fork implies a change in the code, which means that all the miners need to rebuild their hardware. Finally, with every fork, we add an if-else execution code to the client, thereby forcing the system to use forks judiciously. The Ethereum codebase has several of these sprinkled across the codebase. Now imagine this being performed for every repair. Another solution is to simply remove contentious data locally. This approach has several problems. The first problem is that the blockchain protocol is unaware of the repairs. This means that the protocol may still provide, for instance, GDPR violating data to other nodes in the system. Any new node in the system requires the old pruned data to verify the new chain and build the latest state. If all the nodes prune their local chains, then no new node will be able to verify the validity of the chain. Now we present our work, Reparo. Reparo changes the way the chain is validated so that the chain is aware of repairs. Reparo saves the old data in databases and uses them during the chain validation. Any user can request a repair as a transaction. Reparo then leverages the blockchain's consensus to decide whether to apply the repair. Reparo breaks the links in the chain securely so that the long chain attacks or stale state attacks can't be applied to the broken chain. After applying the repair, Reparo ensures that the old and stale unrepaired version of the chain is no longer valid. Let us take an example of Ethereum. A block in Ethereum consists of two parts. The first part is the header. The header contains several fields. We will take a look at some of its fields later. The second part is the body, which is just a vector of transactions. The header has a TX root field. The TX root, marked in yellow, is the Merkle-Patricia trie root of all the transactions in the body, which is marked in cyan. A Merkle-Patricia trie can be thought of as a Merkle trie with 16 children and some optimizations to avoid needless branches. This connects the body to the header. Now, let us take a look at how blocks are connected to each other. The parent hash connects the parent block to its child. The parent hash is the hash of the header of the parent block. This connects blocks directly using a hash pointer. There is a second indirect pointer between two blocks. This indirect pointer is the state root. The state root of a block is the Merkle-Patricia trie root of the world state after applying all the transactions in the current block. Start with the state after applying all the transactions in block B. The Merkle-Patricia trie of this state is present in block B, which is marked in red circle. The new state for block B dash is produced by applying the transactions of the new block B dash on the state present in the parent block B. This creates an indirect second kind of link between two blocks B and B dash. We call this the generic link or the state link. Now, let us take a look at how Reparo works in Ethereum. First, the clients submit repair requests to the blockchain. Let us look at an illustration. The cloud represents the blockchain network, and the machines are clients that send transactions to the blockchain. The normal transactions are represented using black arrows, and the repair transactions are marked in green. A client wishing to repair a transaction, say a contract bug fix, sends a repair request transaction. This is a new transaction type introduced by Reparo. The miners or deciders mine the repair requests like any other transaction in the blockchain. The blockchain network provides the miners with transactions to work on. The miners start mining transactions into blocks. Here we mine another block. Finally, the repair transaction is mined into a block by some miner. Now that a repair request is mined, the miners discuss and deliberate whether this repair is worth fixing. The miners decide whether the repair is worth fixing by discussing is it actually a bug. The community discussions ensue on forums and mailing lists. After deliberation, the miners decide whether the repair needs to be actually performed. We'll take a brief pause here to discuss the repair policy. The repair policy P defines what constitutes a valid repair, such as stateless changes only, which means replace a transaction Tx with a Tx prime such that the state before and after is the same. Or maybe the repair policy says that you should only perform or repair contract deployment transactions. Or the repair policy may say that any hybrid of these two is okay. The repair policy also defines who can approve repairs. For instance, the repair policy can say that the approval rule should be that 90% miners should agree to applying the repair. It can also say that Vitalik and 60% miners must agree. Or a Bitcoin approval policy could say that Satoshi, whatever Satoshi says is the rule. Finally, the repair policy also dictates how to apply the repairs based on what repairs are allowed. For instance, if stateful repairs are allowed, how much gas must be charged, who pays these costs, and other such specs. Based on the deliberation and the policy, the miners show support by adding special vote transactions in their mined blocks. Here, we show the miners showing their support to approve the repair by including the votes for the repair as a transaction in the blocks. On a historical note, this technique was used informally by miners in Bitcoin to show support for SegWit. Now we wait for L blocks to gather all the support. At this point, if there are sufficient votes, then we decide to apply the repair. Otherwise, we simply choose to drop the repair. It's not important. In this illustration, we wait until L blocks are mined after the repair transaction is mined, which is shown in green. If the repair policy P dictates that at least, say 60% of the nodes in the system must support a repair, then we want at least 60% votes in these L blocks. Once this is done, we start repairing the chain. Now we explore how to apply the repairs. We will maintain additional data structures named RDB and ADB, which stand for Repair Database and Approval Database. These data structures are used when applying the repairs and validating a new chain. For the normal blocks where no repairs are being approved, we use the underlying blockchain's validate block function. When a repair is approved, we add information to the databases. When a new node syncs with the network, it is also given these databases. Now let us visualize how we handle the breakage of the links in every block. First, we move the old buggy state into our new databases. Then we apply the repair. At this point, the hash and the generic links break. Next, we build the new state. Starting from the repaired green block, note that the gas cost of all the re-execution must be paid for by someone, say the repair initiator, and all of this will be dictated by the policy. A second note is that these links are not updated in the blocks themselves. The state root in the new red block connects to the repaired state and not the previous block. By breaking links and connecting them in this fashion, we ensure that the hash chain always grows the longest, but the state links always refer to the latest repaired state. Now, when nodes sync the chain, they will simply rebuild the originally mined chain and reapply the repairs on their own. This technique also favors the light clients as they download the state objects based on the Merkle-Patricia trie root in the state root field of the header of the latest block. In general, any blockchain can implement Reparo by building a repair policy and then introducing two new transactions that allow anyone to post repair-related transactions, and then maintaining databases for Reparo, and finally overriding the validate chain, validate block, and validate transaction methods of the underlying blockchain. We implemented a prototype in the Go implementation of Ethereum. We used the transfer function, which is a transaction used to send ethers to another address. Our experiments show that the two new transactions, RepairTX and VoteTX, introduced by Reparo, are comparable to the transfer transaction. We also imported the latest, approximately 26,000 blocks, with a block gas limit of 10 million and observed a deterioration in performance of about 2 to 3 minutes, when compared to the whole import taking about 2.3 hours. Let us take a look at what is the practical impact of Reparo on Ethereum. By implementing Reparo on Ethereum, we can repair the parity bug with just 0.27 ethers, releasing more than 1.5 million times more ethers that was stuck. Implementing Reparo on Ethereum also sets up a mechanism to handle bugs. To summarize, we present a generic repair layer that can transform any proof of stake or proof of work blockchain into a repairable blockchain. After enabling Reparo, the blockchain can repair any transaction, the repairs are publicly verifiable, improve the chain quality by removing malicious content in terms of both illicit data and attacks, and finally help add regulations to blockchains for future adopters of blockchains. Thanks for making it this far. If you would like more details about some of the discussion on immutability and the optimizations that we used, please refer to our paper on arXiv. If you have any questions, feel free to contact any of us. See you in the conference. Bye.